Hello student, good morning. I am Dr. K.Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing chemical thermodynamics. Under that, almost all important terms I have finished. Now I will discuss some important information related to chemical thermodynamics. Last class I have discussed effect of temperature on spontaneity, standard free energy, second law of thermodynamics, third law of thermodynamics, and zeroth law of thermodynamics. Zeroth law of thermodynamics I have finished, and just I want to brief it. Zeroth law of thermodynamics states that if two bodies have separately equality of temperature with a third body, they have equality of temperature with each other. Again I am telling, if two bodies have separately equality of temperature with a third body, they have equality temperature with each other, means all three will have same temperature. This is actually zeroth law of thermodynamics. Now some additional information I want to discuss. First, Joule-Thomson effect. Joule-Thomson effect. When a real gas is allowed to expand adiabatically from a region of high pressure to a region of low pressure through a fine hole or porous plug, it is accompanied by cooling. If gas is allowed to expand adiabatically from a region of high pressure to a region of low pressure through a fine hole or porous plug, it is accompanied by cooling, except hydrogen and helium, which get warmed up. This is the exception. Question is asked. In case of hydrogen and helium, there will be warming. They get warmed up. Hydrogen and helium get warmed up. Okay, this is exception. Generally, there will be cooling. During Joule-Thomson effect, during this process, enthalpy remains constant. Remember, enthalpy H or delta H. Remember, during this process, enthalpy remains constant. It is therefore called isoenthalpic process. Joule-Thomson effect, this process is called isoenthalpic process. Why? Because enthalpy remains constant. The actual change in temperature on expansion of gas is expressed in terms of Joule-Thomson coefficient. The actual change in temperature on expansion of the gas is expressed in terms of Joule-Thomson coefficient, mu. It is denoted by mu, and mu is equal to del T upon del P at constant H. H means enthalpy. Then what is actually Joule-Thomson coefficient? Then Joule-Thomson coefficient, it is represented by mu, and mu is equal to del T upon del P at constant H. H means enthalpy. It is the means what is actually Joule-Thomson coefficient? then it is the temperature change in a degree produced by a drop of 1 atmospheric pressure. Drop of 1 atmospheric pressure when the gas expands under condition of constant enthalpy. Again, I am repeating. Mu, that is a Joule-Thomson coefficient, is defined as the temperature change. It is the temperature change in degrees produced by a drop of 1 atmospheric pressure when the gas expands under condition of constant enthalpy. Delta T upon delta P. It means 1 per 1 atmospheric pressure, because you are dividing by delta P. But this should be at constant H enthalpy. Then it is the temperature change in degrees produced by a drop of 1 atmospheric pressure when the gas expands under condition of constant enthalpy. Now further I am telling you for what is the value of mu. Then mu has 3 values you can tell. First, for cooling, that time mu will be positive. For cooling, mu is equal to positive. Why? Because del T and del P both will be negative. Temperature change will be there, it will drop. Temperature change means temperature will decrease. Delta T will be negative. And this delta P is also will decrease. Then both delta T and delta P will be negative. Hence both negative will be cancelled. Hence it will be positive. Mu value will be positive in case of cooling. And heating, just reverse, mu is equal to negative. Why? Because delta T will be positive. Heating time, temperature will increase. Hence delta T will be positive, but dP will be negative. Pressure will decrease, that is the negative. But temperature will increase, that is a positive. Hence finally it will be negative. Upside positive, down negative. Finally it will be negative. Then for heating, mu will be negative. Mu is equal to negative value. Negative. And mu is equal to 0. Third value I am telling mu is equal to 0. What does it mean? Mu is equal to 0 means del T is equal to 0 for any value of dP. dt will be 0. Mu is equal to 0 means change in temperature will be 0 for any value of dP, change in pressure. That is, there is neither cooling nor heating. The temperature at which a real gas shows no cooling or heating effect on adiabatic expansion, that is the mu is equal to 0, is called inversion temperature. This is very, very important term. Condition already discussed. Again I am telling you, the temperature at which a real gas shows no cooling or heating effect on adiabatic expansion, that is mu is equal to 0. That is the condition for adiabatic expansion. Mu is equal to 0. It is called inversion temperature. Below this temperature, it shows cooling effect, while above this temperature, it shows heating effect. Inversion temperature means below this temperature, it shows cooling effect, while above this temperature, it shows heating effect. Correct? Then inversion temperature means mu is equal to 0, you remember. Most of the gases have inversion temperature above room temperature. Most of the gases have inversion temperature above room temperature. H2 and He means hydrogen and helium have low inversion temperature, that is minus 80 degree centigrade and minus 240 degree centigrade respectively. That's why they show heating effect at room temperature during adiabatic expansion, because its inversion temperature is very less, minus 80 degree centigrade for hydrogen and minus 240 degree centigrade for helium. They have low inversion temperature. That's why they show heating effect at room temperature during adiabatic expansion. For ideal gases, mu is equal to 0 at any temperature. For ideal gases, mu is equal to 0 at any temperature. Now, next term, additional information I am telling you. Heat capacity and molar heat capacity. Already I discussed heat capacity and molar heat capacity. Now, little more I want to discuss. Heat capacity of a substance. Heat capacity of a substance is defined as the amount of heat required to raise the temperature of the substance through 1 degree centigrade. If the amount of the substance taken is 1 gram, it is called a specific heat, and if it is 1 mole, then it is called molar heat capacity. Correct? Both are heat capacity. Then heat capacity, when 1 gram you are considering, temperature raised by 1 degree of 1 gram, and temperature raised by 1 degree for 1 mole. Then it is called molar heat capacity. If 1 gram is considered, then heat capacity. When 1 mole you are considering, then molar heat capacity. And it is expressed C means heat capacity. Then C is equal to Q means heat, divided by T2 minus T1, change in temperature. Then C is equal to Q upon T2 minus T1, high temperature minus low temperature. That is the delta T. Simply you can tell C is equal to Q upon delta T. Correct? And also you can tell for a very small change, in the place of Q, you can tell del Q. And for the delta T, you can write del T. Actually, delta means big change. Change is there, but delta means more change, and del means less change, and only D means differentiation. Okay, that also coming under less change only. For a small change, then you can tell C is equal to del Q upon del T. As Q is not a state function, you remember, as Q is not a state function, therefore C is also not a state of function. Remember, question is asked. As Q is not a state function, therefore C is also not a state function. Hence, to know the value of C, the condition such as constant volume or constant pressure have to be specified, which define the path. Thus, there are two types of heat capacities, which are: first, CV means heat capacity at constant volume. Second, heat capacity at constant pressure, CP. Then CV means heat capacity at constant volume. CP, P means pressure, heat capacity at constant pressure. Again, I want to repeat one sentence because that should be clear, that as Q is not a state function. Therefore, C means heat capacity is also not a state function. Hence, to know the value of C, how will you come to know the value of C? The conditions such as constant volume or constant pressure have to be specified, which define the path. Thus, there are two types of heat capacities, which are heat capacity at constant volume Cv and second heat capacity at constant pressure Cp. Now, according to the first law of thermodynamics, always you remember first law of thermodynamics, that is the del Q is equal to del E plus P into del V. Okay, or delta also you can tell, no problem. For the small change, del is written. Then del E is equal to del E plus pressure into change in volume, dV. Change in volume. dV means change in volume. Then this is actually mathematical form of first law of thermodynamics. dQ is equal to dE plus P into dV. D means here change in volume. Okay. Then you can directly tell del E that is equal to del E is equal to del E plus pressure P into delta B. Delta B or dV you can write. Okay, change only. This is actually first law of thermodynamics. Also you can remember dE is equal dQ is equal to dE plus P into dV. P into dV. Energy you have to add. dE means change in energy. Or delta also you can remember. Anyway you can tell delta Q is equal to delta E plus P into delta V. Then pressure into delta V or dP, that is the work done. That is the work done. Then now what is the C value? Then I told you C is equal to dQ upon dt. dQ upon dt. Then in the place of dQ, now you can write dE plus P into dV. C is equal, now Q value only, value of Q you have to write. Then Q is equal to, I told you, del Q is equal to del E plus P into dV. That value you have to put here in the expression of C. Then it will come in the place of Q we are writing now del E plus P into delta V divided by delta T. Then this is the expression for heat capacity. Now I told you it is of two types, at constant volume and at constant pressure. Then just you see the equation. C is equal to dE plus P into dV divided by dt. Then now when volume is constant, then what will remain? dE plus P into delta V. Then V is equal to 0. Then what will remain? Only dE will remain and down dt will remain. Then this happens at constant volume. At constant volume. Then you write in the place of C, you write CB. V you write a small b down. Means heat capacity at constant volume. That is equal to del E upon del T. And in bracket, down you write B. Correct? P into dV. B was 0. That's why this term gone. P into 0 means 0 only. Then CB is equal to del E upon del T at constant B. Or you can write CB is equal to dE upon dt. For ideal gas you can write. Then this is the expression for heat capacity at constant volume. Heat capacity at constant volume CB is equal to dE upon dt for ideal gas. Now at constant pressure what will happen? Then now again you see the consider the same condition formula. C is equal to dE plus P into dV upon dt. Then pressure is constant. Then now in that expression, how will you write? Then in the place of C, now you can write Cp. Down the C, you write a small p. P means pressure. Cp. Then now what will happen? You divide dt with both term. You make it separate. d upon dt plus p dv upon dt. Correct? You can write. You can write in this way also, because dt is in down. dE plus p into dv divided by dt. It means you are dividing by dt for both term. dE also you are dividing, and p into dv also you are dividing for both term. Hence you can separately you can write. Then dE upon dt at constant v. Already you have written that. I finished. This dE upon dt, first term, but this you are using at constant pressure. Hence down you write p dE upon dt, in bracket down you write a small p, plus now what is remaining? P into dv upon dt, p into dv upon dt. Then p is a constant, you write outside, and dv upon dt, that you write in bracket, and down you write p, because you are considering at constant pressure. Then for both term you introduced constant p. Then del E upon del T at constant p, means dE upon dt, in bracket you write, down you write p, means at constant pressure, plus p into dv upon dt at constant p. Then this is actually Cp. This is the expression for Cp. Cp is equal to dE upon dt at constant p, plus p into dv upon dt at constant p. Means in the case of this thing, heat capacity at constant pressure, two terms are there. One term involves energy E, and other terms involves a change in volume dV. Correct? dV, delta V, anything you can understand. Okay. Then this Cp includes two terms. One term is for energy and other term is for volume, change in volume. But in the case of Cv, only one term is there, that is for energy. Del E upon del T at constant V. Only one term is there for Cv, but for Cp two terms are there, energy term as well as volume term. Then now actually one important relation I am going to derive. Easily you can derive. Then actually you know H is equal to E plus PV. H means enthalpy. Enthalpy is equal to E plus PV. Already I discussed. Enthalpy is equal to E plus PV. P means pressure, V means volume. Then now just to differentiate it, this relation you differentiate it with respect to temperature, then what you will get? You will get del H or dH, you can add dH upon dt at constant P, that is equal to dE upon dt at constant P, plus P into delta V upon delta T at constant P. All are at constant P. Enthalpy H is equal to E plus PV. Now we are differentiating with respect to temperature. Then H will become dH upon dt at constant P. That is equal to dE upon dt at constant P, plus P into B is there, then P is constant. Then you write outside only P. There is no differentiation for constant. Then P you can write outside. P into dV upon dt at constant P. Then this also you can write that delta H upon delta T at constant P. In bracket, write delta H upon delta T in bracket. Down you write a small p. That is equal to delta E upon delta T in bracket. Down you write a small p plus p into delta V upon delta T at constant p. Down you write a small p. This is very, very important relation. Now just after that, this relation you are knowing, and already Cp and Cb expression I told you. Then here that Cp equation I told you, Cp belongs to Cp consists of two terms, and delta H also consists of two terms. And now what you have to do, that this is Cp is equal to delta H upon delta T at constant P. Correct? Cp, because Cp is equal to delta E upon delta T plus P into delta B upon delta T as constant P. Already I have discussed. Then here you can write same things for the Cp. Now you can write delta H because both expressions are same. For Cp and for delta H, now what you have written, both are same expression. Hence in the place of Cp, you can write delta H upon delta T, because this expression also consists of two terms, E and V. E and V same, both are same. Hence in the place of Cp, you can write delta H upon delta T at constant P. Correct? You can write. Then Cp is equal to delta H upon delta T at constant P. Or you can write simple way, Cp is equal to dH upon dt for ideal gas. Same things. You remember, dH upon dt, that is equal to Cp, and Cp is equal to del E upon del E upon del T at constant P plus P into del B upon del T at constant P. Correct? Now here again you can see further, H is equal to E plus PV. H is equal to E plus PV, same equation. And PV is equal to what? RT for 1 mole of gas. PV is equal to RT for 1 mole of gas. Then H is equal to E plus PV means you can write E plus RT. In the place of PV you can write RT. Then now you got H is equal to E plus RT. E plus RT. Then now again you can take differentiation with respect to temperature. H is equal to E plus RT. Then just to differentiate with respect to temperature, then H will become dH upon dt. That is equal to E plus RT. Then again it will become differentiation with respect to temperature, d upon dt. Correct? E you can write dE upon dt plus R is constant, you know. Then R, there will you can say differentiation of constant. Then R is equal to R into T, RT. Then R will be as it is. dt upon dt, both will be cancelled. Hence only R will remain. R will remain. Then delta H upon delta T is equal to delta E upon delta T plus R. Plus R. RT was there, but with respect to T, differentiation with respect to T, the TT will be cancelled. dt will be cancelled. Only R will remain. Then now see dH upon dt. For that you can write Cp, and for dE upon dt you can write Cb. Correct? Cp is equal to, just now I told you, delta H upon delta T, that is equal to Cp. Same way, delta E upon delta T, that is Cv. Then Cp is equal to Cv plus R. In the place of delta H upon delta T, you have written Cv. That is equal to delta E upon dt, that is equal to Cv plus R. Then it means Cp is equal to Cv plus R. And then you can also write Cp minus Cv, just to bring it Cv left side. Then Cp minus Cv is equal to R. This is very, very important relation. Very, very important relation. Cp minus Cv is equal to R. And here you should remember Cp is greater than Cv. Why Cp is greater than Cv? Then you should understand in the Cp term, two terms are there. One is energy term, other is volume term. It means if you want to raise the temperature of any system by 1 degree, centigrade at constant pressure, then more heat will be required, because some heat will be used up in changing the gas. Suppose gas you are heating and you want to increase by the temperature by 1 degree. Then if you will heat, then some heat will be used up in expansion. In expansion, when gas will expand, for that heat is required. Then some heat will be used up in expansion, and then it will raise the temperature by 1 degree. Correct? Hence more heat will be required here. But at constant volume, if you want to increase the temperature by 1 degree, then there will be no expansion. No expansion. Only temperature you have to rise by 1 degree. Then there less energy will be required, less heat will be required. But in case of Cp, because both will be done, expansion as well as 1 degree raise of temperature, hence more heat will be absorbed in this case, in case of Cp. That's why Cp is always greater than Cv, you remember. And that's why Cp minus Cv is equal to R. Its value will be fixed, R value. Hence Cp is greater than Cv by the gas constant R. And what is the value of R? Then approximately 2 calories. 2 calories, 1.98. 1.98 is exactly, roughly you can tell, 2 calories. Or another value is there, R is equal to 8.314 joule. Any one, both value you can keep in mind because both are important. R is equal to 2 calories, means exactly 1.98 calorie. And other value is 8.314 joule. And what is the ratio? Cp upon Cv. The ratio Cp upon Cv, that is represented by mu, and not mu, lambda, just like a small y. Cp upon Cv, that is equal to lambda. Then what is its value? Lambda value for monatomic gas, for diatomic gas, for triatomic gas. They all have separate value. Then gamma or lambda, gamma you tell lambda, this only lambda you tell, lambda only Cp upon Cv, just like a small y. Okay. Then here lambda is equal to Cp upon Cv, and for monoatomic gas like helium and argon, its value is 1.66. You remember, for monoatomic gas, this is the gas but only one atom is there, not 2 or 3. Helium, neon, argon, krypton, xenon, radon, all are monatomic gases. Then for helium or argon, these are monatomic gases. The example, its value is 1.66. And for diatomic value, that is different, like H2. 2 atoms are there of H. O2, 2 atoms are there for oxygen. CO, carbon monoxide, 2 atoms are there, 1 C, 1 O. Its value is 1.40, less, little less. And for triatomic, it is further less, 1.30. 1.30. Example, CO2, triatomic gas, 1 carbon, 2 oxygen, H2S, 3, 2 hydrogen, 1 sulfur atom, total 3. then its value is 1.30. Question is asked. Okay, Cp, what is the value of this lambda? Lambda value, that is equal to Cp upon Cv. Okay, then that is equal to 1.66 for one monoatomic gas, and for diatomic 1.40, and for triatomic 1.30. Now, application of first law of thermodynamics to different type of processes. This is also very, very important. Already I have told what is the first law of thermodynamics. I told you, energy can neither be created nor be destroyed. Only it can be changed from one form to the another form. And its mathematical relation is Q is equal to E plus PV. Simple way. Q is equal to E plus PV, or dQ is equal to dE plus P into dV, change in volume. Then what is its application in different system, in different process, I am telling you. First, for an isochoric process, and for an isochoric means volume will not change. Volume will not change. Volume will be constant. For an isochoric process, as volume is kept constant, delta V is equal to 0. No change in volume. Change in volume is equal to 0. Means dV is equal to 0 or delta V is equal to 0. Hence, in the expression, Q is equal to E plus PV. And there V, delta V conduct. Delta is equal to delta E upon delta V. Then there is no change in volume. Hence this term will be P into delta V term will be 0. Then dQ is equal to dE. dQ is equal to dE. Correct? This is very, very important. dQ or delta E also you can tell. Delta is equal to only Q. Both will be equal. Q is equal to delta E or delta is equal to Q. Both are same because V value is 0. Then now you will get, because the P into delta V is 0, hence P into delta V term becomes 0. Hence dQ is equal to dE or dE is equal to dQ. Same things. Hence delta E is equal to QV. Correct? Delta is equal to QV. Because in the relation Q is equal to E plus P into V, then V is 0. Hence Q and V, E will remain, both are equal. Hence delta E is equal to delta is equal to QV. Okay, QV, V means at constant volume. Now this I told for the isochoric process. Isochoric means when volume was constant, and you applied only in the first law equation is there, on that you have applied this you can say V is equal to 0, you have applied here in first law of thermodynamics. Now in second system is isobaric process. Isobaric process means pressure is kept constant. Isobaric, bar means pressure, remember. Then for an isobaric process, pressure will be kept constant. Then now when pressure will be kept constant, then first law, what is the first law? The first law, you know that delta E is equal to Q minus P into delta V. Or one way only you keep in mind, Q is equal to E plus PV, and P is constant. P is constant. Then what will remain now? Q is equal to delta E plus P into delta V, and P is constant. Then these two term delta E plus P into delta V, that is called delta H, that is called change in enthalpy. Change in enthalpy is equal to power, H is equal to E plus PV. Hence, there's delta E plus P into delta V, that is equal to delta H. Hence you can write Q is equal to delta H. QP, because pressure is constant. That's why you are writing QP. P is constant. That's why QP is equal to delta H. But in the case of this constant volume, it was QV because volume was constant. Then in the Q, down you write a small v. Then QV is equal to delta E in case of isochoric process because volume was constant. In isobaric process, P is constant. And the same equation, first law, you can write in the place of delta E plus P into delta V, that is actually H, enthalpy. Hence dQ is equal to dQ at constant pressure is equal to delta H. And third, that is isothermal process. Here temperature will be constant. At constant temperature for an ideal gas, what will happen? Because temperature is constant, then delta E value will be 0. There will be no change in temperature, then delta will not change. Then delta E value will be 0. Hence in the same reaction, same equation, first law of thermodynamics, only in that equation in the place of delta E you write 0. Then only two terms will remain, Q and P into delta V. Correct? Only this term will, because delta is equal to 0, E is equal to 0. Then Q is equal to P into V or P into delta V. Correct? Then here delta is equal to 0. Then what will happen? Now we have to see. Here at constant temperature means isothermal process. Delta is equal to 0, you remember. Then what will be the W? Work. If gas will, because this temperature you are keeping constant. Temperature you are keeping constant, then there will be no change in energy. Delta is equal to 0. Under this condition, what is the work for expansion? Expression already I have discussed. Work for, I can say, expansion, WEXP you can write. Work done during expansion, that is equal to minus 2.303 nRT log V2 upon V1. V2 means V2 is greater than V1, volume. V1 is less volume, V2 is more volume. Means volume change from V1 to V2. Then its expression will come W work done during expansion, EXP. Shortcut you can write W and down EXP, that is equal to minus 2.303 nRT log. Actually it was ln. Ln you have converted into log. That's why you have multiplied by 2.303. And minus means work is done on system. That's why it is minus. Correct? Because gas system will do the work, then their energy will decrease. Correct? Then work done by the system, not on. Work done by the system, then it will be minus. And volume change from V1 to V2, expansion. Then V2 write upside, V1 write down. Okay, V1 to V2. Then this you remember, expression is very, very important. W expansion is equal to minus 2.303 nRT. N is the number of moles. RT, R is gas constant, T is temperature. Log V2 upon V1. Same, you know, now in the place of V2 upon V1, same expression you can write in term of pressure. You know Boyle's law. Boyle's law, that V is inversely proportional to P or P is inversely proportional to V. Just reverse way. Hence in the place of V2, reverse way you write. In the place of V, you write P. In the place of V, up and down. And where is it 2? There you write 1. Where is 1? There you write 2. Means now it became P1 upon P2. There it was the V2 upon V1. Now V became P, pressure. But here it will be reverse. Then in the place of 2 you write 1. And in the place of 1 you write 2. Simple way, reverse way. Then now we will get minus 2.303 nRT log P1 upon P2, because in the first expression all thing was same, only V2 upon V1. Now you are writing P1 upon P2. Remember, in the place of V you write P, and in the place of 1 you write 2, and in the place of 2 you write 1. And one more process is there, adiabatic process. Then adiabatic process means delta Q is equal to 0. Adiabatic process means neither heat will come to the system nor it will go outside the system. Whatever either you can say less or more, it will be only in the system. It will not go outside, heat will not go outside, and if it is less, it will not take from the outside. Okay, that is the adiabatic process. Here delta Q is equal to 0. Neither heat will enter nor it will leave. Okay, delta Q is equal to 0. Then in the first law equation, here dq value is equal to 0. Then what is remaining? Only two terms will remain, del E and del W. Only two terms will be there, because del E is equal to del Q. You know, first law, Q is equal to E plus PV. PV is equal to work done. Pressure into change in volume. Pressure into change in volume, that is the work done. And in the place of P into delta, we can write W also. Then here same way, dq is equal to DE. dq is equal to DE plus dW. W. Anyway you can write, or you can also write DE, that is equal to dq plus dW. Okay, change in or work done only you can write. DE is equal to dq plus dW. Then here Q is equal to 0. Then DE is equal to dW. DE is equal to dW or delta W. Okay. Then this is the actually for adiabatic process. Then here we know del E upon del T. Del E upon del T, that is equal to CB, you know. Del E upon del T is equal to CV. Then what is the del E? Del E is equal to CV into dt. CV. dE upon dt, that is equal to CV. Then what is the dE? Then d is equal to CV into dt, cross multiplication. d is equal to CV into dt. And hence you can write in the place of dE, you can write CV into dt. Then here you have seen that dE was dW. dE was dW. Then now in the place of dE, you can write CV into dt. Hence you will get W is equal to, or delta W is equal to CV into dt. That is for 1 mole of gas. For 1 mole of gas, dW is equal to CV into dt. This is for 1 mole of gas. But for n mole of gas, you have to multiply by n, small n, for 1 mole of gas. Then now you can write dW is equal to n into CV into dt. dW is equal to n into CV into dt for n moles. And this expression you can integrate. This is a del W is there. Del W means very less work done. Then if temperature is more, T1 to T2, it's suppose more, T1 to T2, T1 means suppose 10 degree to 50 degree. So we did here, what we calculate del W, that is for very small change. Then you can integration, you can do for more change. Then from T1 to T2, then same relation you can integrate. Then you will get W is equal to sine of integration, limit is T1 to T2, down T1, upside T2. That is equal to n into CV into dt. Correct? Then CV value is a constant, its value is fixed, n value is also fixed. Hence you can keep outside of integration. Then you will get total work done W is equal to N into Cv, and in the place of dt you can write T2 minus T1. T2 minus T1, because limit is there, down is T1, upside T2. Hence higher minus lower, up minus down. Up is T2, down is T1, higher minus lower. Then you can write work done. What total work done W is equal to N into Cv in bracket T2 minus T1. Okay. Then this I have discussed. We can say all applications of first law of thermodynamics to different types of process. Okay. Today I am stopping only here. Next class again I will continue. Thank you.